Alrighty, folks. So today we're talking about section 3.3, which is going to be a fairly short one because there's really only two things in this section, and that's the product and quotient rules. So the summary of this section is really easy. It's the product rule that says if we have f times g and we want to take the derivative of it, that's going to be the derivative of one of them times the other plus the derivative of the other one times the first. Right? So both derivatives get in there, but they each get in their own piece where the other function is left alone for that term. Right? And then we have the quotient rule, which says that if we have f of x divided by g of x, and we want to take the derivative of it, that is going to be, and I'm going to do the very silly rhyme, which is the only thing that lets me keep it in my head, which is low d high, so the function on the bottom times the derivative of the function on the top, minus high d low, which is the derivative on the top times the derivative, or the function on the top times the derivative of the function on the bottom, over the square of low we go. Right? So the quotient rule, it's not too important to remember because it doesn't matter what order you do it in, as long as you have two terms and each of the terms has one derivative and they're a different derivative. It doesn't matter whether you do the derivative of f first or the derivative of g first. However you do it is fine. With the quotient rule, it's very important because we have a negative here, and it matters which one comes first. So it's always going to be low d high minus high d low over the square of low we go. So the one on the bottom times the derivative of the one on the top minus the one on the top times the derivative of the one on the bottom over the square of the one on the bottom. All right? So we're going to get some practice in. So let's start off with something fairly simple. Let's have f of x is x times e to the x. Right? So this one is a product rule, right? This thing as a whole isn't one of the ones we know already, right? But it is a product of two things we know, right? So in this case, we have x and we have e to the x. And when we take the derivative of x, we get 1. And when we take the derivative of e to the x, we get e to the x back, right? So the derivative of their product is going to be the derivative of one of them times the other one by itself, right? So this is, actually, let me write this up more explicitly. This is the derivative of x times e to the x plus x times the derivative of e to the x. Right? So we already figured out the derivative of x was 1. And the derivative of e to the x is just e to the x. So we get e to the x plus x e to the x. All right. Let's see. We can, well, let's get a basic quotient rule in here. Let's do f of x equals e to the x divided by x squared. Right? So this is another one again where we've got a basic power function and that we know how to take the derivative of, and we've got e to the x that we know how to take the derivative of, and we have a quotient of those two pieces, right? So in this case, high is e to the x, and low is x squared, right? So the derivative of their quotient is low d high minus high d low over the square of low we go. So this is going to be x squared times the derivative of e to the x, which is just e to the x, then minus e to the x times the derivative of x squared, which means we use the power rule to bring that 2 down, and it changes the exponent to a 1, and when the exponent's 1, you don't actually have to write it down. And then x squared squared is x to the 4th. Right, so if we wanted to simplify this, there's a couple things we could do. We could maybe factor, right? There's an x e to the x in both of these, leaving us with an x minus 2 up here, all over x to the 4th. And factoring means we can cancel. So e to the x, x minus 2 over x cubed. And yeah, so that lets us simplify it a little bit. Right? We could have, this isn't the most unsimple thing. Usually we like to put constants like 2 ahead of everything else, but otherwise that would also be a perfectly fine way to end it out. Let's see. And it doesn't just have to be individual power functions, right? It can be anything we found the derivative of. So let's say we have x cubed minus 2x squared plus 11x all over x e to the x. Right, so low is x e to the x. High, whoops, I'm going to leave room. I'm going to put d low, right, because that's part of our rhyme. We actually figured that out up here. E to the x plus x e to the x. Right, high is x cubed minus 2x squared plus 11x. Right, d high, we're going to have to use our power rule from last time. And give myself a little bit more room here. Right, so for the first term, we're going to bring that 3 down and move the power down to a 2. For the next term, we're going to take that 2 and multiply it by the coefficient to get 4 and bring the power down to a 1. And then for the 11, we're going to bring the 1 down. 1 times 11 is just 11. When we take the power down by 1, it becomes x to the 0, and x to the 0 is just 1. Right? So, if we make ourselves a little cheat sheet over here of all the pieces, we don't necessarily have to go through all the steps that we did here. We can remember that it's low. I'm actually going to give myself more space. It's low d high minus high d low over the square of low we go. So we could simplify that if we really wanted. There's not really anything calling us to do that. We can just leave it the way it is. Especially since there's not going to be, like, we could maybe cancel out an e to the x, but that's not actually going to make our lives any simpler. So that's a perfectly fine final answer, right? Quotient rules can tend to get to looking kind of nasty. So next up, we're going to say that P is equal to V squared R over big R plus little r squared. And this is a formula involving voltage and resistance and some stuff. But really, I just want to use it to illustrate what to do when we have a lot of variables, right? So we might have a problem that asks, find dp dv, right? And this is one of the places where Leibniz notation is super important because we have a bunch of variables over here, right? It's not just an x involved here. We've got a v, we've got a capital R, and we've got a little r. Where if we just said find the derivative of p, we'd have a little bit of problems because we don't know what the variable is, right? But Leibniz notation tells us exactly which of those letters counts as a variable for our purposes, right? And what that means for us is that we get to treat the rest of the letters as if they were constants, right? So then we can sort of rewrite this as p equals this constant times v squared. And in this case, we could have actually done this problem last section, right? Because if v is the variable that we care about, this is just a power function. All right. So we can say dp dv equals 2 times the constant that was already there times v to the 2 minus 1, but that's just 1, so it's just v, right? So if we wanted to find dp dv, we could have done that last time. It's just a power function with a really weird looking constant, right? If our problem is find dp dr, right, that looks like we might need the quotient rule, right, because r is on the bottom of a fraction. And for our purposes here, let's see. I was going to say we might be able to do something different, but for our purposes here, we'll treat it like we need to use the quotient rule, right? It's on the bottom of a fraction. Quotient rule is for fractions, so let's do it that way, right? So in that case, high is v squared r. Low is r plus little r squared. Now, we've got a little bit of a problem here in that r is inside of a composition as it's written like this. And eventually we'll have rules to deal with that, but we don't have them yet. So what we really need to do to make this workable with the tools that we have so far is we need to multiply that out. So it's just a polynomial, right? Now, d high in this case is nice and simple because there's no little r's there, right? So if our problem is to find the derivative with respect to little r, every letter that's not a little r is a constant, right? And if we remember from last section, the derivative of a constant is 0, right? And d low, this is just a polynomial, right? So capital R squared here is just a constant. This is just a linear term, so we just get the coefficient. And this guy becomes 2r, right? We bring that 2 forward and we drop the exponent by 1. Right, so this is 2r plus 2 little r. Right, so that means that dp dr is low, which we can put it in simplified form here because we've already taken the derivative of it. So low d high minus high, dang it, I want to rewrite all of that. There we go. So low d high minus high d low over the square of low we go. Right, and this one we can simplify a little bit, if nothing else, because multiplying by 0 makes that go away. So we get negative VR squared times 2 capital R plus 2 little r, all over capital R plus little r to the 4th. Right? So since our little r was on the bottom of the fraction, we do in that case have to use the quotient rule, right? So I largely wanted to emphasize here that, one, if you've got multiple variables, Leibniz notation is very important to tell you which one is the actual variable for our problem here. Here in Calc 1, we're not dealing with multiple variables at a time, so we have to say that one of them is the real variable and the others are just constants for the moment, right? So we need to do that. The other thing is that a fraction doesn't automatically mean quotient rule, right? Sometimes it means, sometimes the denominator of that fraction is all constants. And if your denominator is all constants, then you can use the constant multiple rule instead of the quotient rule, and it saves you a lot of time. You could also use the quotient rule. There's nothing saying you can't. You're just going to get a lot of stuff that cancels out, and you're going to do more work than you really need to. So this was the product and quotient rule. We're going to take a brief diversion to talk about some applications of derivatives next, and then after that we're going to get even more rules, because we're not quite at the end of our rules or lists of known functions yet. But that'll be for next time, and I'll see y'all then.